Good morning, students. In previous lecture, we have learned about the Bohr's theory. In that topic, we have solved up to equation 5. Once again, we recall what we have learned in the previous lecture and we can continue with that. We are in the topic Bohr's theory. In Bohr's theory, we have considered the phenomena of transfer of energy from a moving charged particle to the electron of the surrounding medium. That means we have considered a charged particle which is represented with Ze. Now, while assume this charged particle is moving along the x-axis. Okay, this charged particle is moving x-axis. While the charged particle is moving with x-axis with some velocity v, it is going to share energy to the electron which is present at rest. So in this topic we are going to know how the charged particle is sharing its energy to the stationary electrons which are present around it while moving with velocity. Okay. Then in this topic, initially we have considered the transfer of momentum from the charged particle to the electron, and we have represented it as P is equal to integral minus infinity to plus infinity. Here P represents the transfer of momentum from the charged particle to the electron. And we have represented it as P is equal to integral minus infinity to plus infinity Ze square by 4 pi epsilon naught R square into sin theta dt. Okay, here R represents the distance from the charged particle to the electron. Okay, here R represents the distance from the charged particle to the electron, and here A represents the impact parameter. Okay, so here first initially we have considered the transfer of momentum from the charged particle to electron, and we have learned it as equation 1. Then we have considered equation 2. From the angle theta we have considered the equation, that is 1 by r square is equal to sin square theta by a square, and by substituting in the momentum equation, finally we have derived P is equal to Ze square by 2 pi epsilon naught into AV. Then after deriving the final equation for the transfer of momentum, then we have considered the kinetic energy. How the kinetic energy is transferred from the charged particle to electron, and we have denoted it as T is equal to P square by 2m naught. Already we know the value of P from and in previous lecture we have denoted it as equation number 4. So already we know the value of P from equation 4. Just by substituting P value in this equation, we have derived finally T is equal to Z square e power 4 by 8 pi square epsilon naught A square V square into m naught. So up to here we have covered in the previous lecture. Okay, we have covered up to equation 5 in previous lecture. Now today we are going to continue with this. Next, after deriving equation 5, that is transfer of kinetic energy from the charged particle to stationary electron, is denoted by T is equal to Z square e power 4 pi 8 pi square epsilon naught, okay, A square V square into m naught. Now next we are going to consider a cylindrical shell of electrons of radii A and A plus dA. Okay, we are going to consider a cylindrical shell. Okay, we are going to consider cylindrical shell. And this cylindrical shell consists of electrons. Assume this cylindrical shell consists of electrons, and the radius of this cylindrical shell is here from the center to here at any point on this gives R, and whereas from here to here the outer layer of the shell is nothing but dA. So the radius of this cylindrical shell is A and A plus dA, and length of this shell is denoted by dx, where the electrons will travel from one point of the shell to another point. Now assume that there are 2 pi NaZ dA dx electrons per length of this shell. Now we are going to assume, okay, the 2 pi NaZ dA dx electrons are present per dx length of the cylindrical shell. Per here dx means here total length of the shell, dx length of the shell. In this equation, here n you are observing, okay, you know the value of pi, and here n you are observing. Here n represents the number of atoms present per unit volume. Here n represents number of atoms per unit volume. Per unit volume. And here A you are observing. Here A is nothing but impact parameter. Impact parameter means the distance from this point on the x-axis to the stationary electron. That means the closest path. Okay, from the charged particle to the stationary electron. Moving the charged particle to the electron is nothing but impact parameter. Here A represents the length. So here A is nothing but impact parameter. Impact parameter. So what do you mean by impact parameter? Okay, it is nothing but the closest distance to a stationary electron to the moving charged particle on the x-axis, nothing but impact parameter. And then Z you are observing. Okay, what do you mean by Z here? Atomic number. Z represents atomic number. Atomic number. Atomic number means number of protons in an element is nothing but atomic number. Then dA. dA is nothing but radii. Okay, from this point to this, nothing but dA. And dx. dx represents the length of the shell. Okay, length of the cylindrical shell. Length of the cylindrical shell. Cylindrical shell. Okay, so after deriving equation 5, then we have considered a cylindrical shell. Okay, and in that we are assuming that it is completely filled with electrons, and we have assumed that the radius of this cylindrical shell is A and A plus dA. Okay, here A represents from the center point to any point on the inner layer. Okay, this is nothing but A. From here to here point, this point represents A plus dA. Okay, so the radius of cylindrical shell are A and A plus dA. And we have assumed that there are 2 pi NaZ dA dx electrons are present per unit per dx length of the shell. That means overall this entire surface, how many number of electrons are present in this shell? 2 pi NaZ dA dx electrons. That means if you add all these parameters, then you are going to get the total number of electrons present over entire volume of the shell. And we have learned each and every parameter. Here n represents number of atoms present per unit volume. Here A represents impact parameter, Z represents atomic number, dA represents the radius, and dx represents the length of the cylindrical shell. Now we are going to consider the energy transferred from charged particle to a cylindrical shell. Okay. Now we are going to consider, as I have said, that electrons are present in the shell. Now while the charge is moving, okay, here Z is nothing but charge. While the charge is moving, it is transferring its energy to the electrons. So now we are going to consider the equation which represents the transfer of energy from the charged particle Ze to the electrons present in the shell, and it is given by dE is equal to, okay, dE is equal to T 2 pi NZA dA dx. So the energy transfer from charged particle to a cylindrical shell is given by dE is equal to T. Here T represents the kinetic energy. 2 pi N means number of atoms. Okay, number of atoms per unit volume. Z atomic number. A represents the impact parameter. dA represents the radius, and dx represents the length. So this overall values of this equation gives the transfer of energy from the charged particle to the electron present in the shell. Now the energy lost per unit path of length is given by, that means while transferring energy it will lose, that means the energy lost can be happened. So the energy loss per unit path of length of the particle is given by, here as I am saying that energy is losing, so I am representing with minus dE by dx is equal to 2 pi NZ integral A minimum to A maximum dA ZE. So this equation represents the loss of energy per unit path length. Okay, that means per unit path length of the total length, how much energy is losing can be represented by the equation 2 pi NZ integral dA dA. And you know each and every parameter. Here dE represents the transfer of energy from the charged particle to the electron present in the shell, and minus dE by dx represents the loss of energy, okay, per unit length, is equal to 2 pi. N represents number of atoms per unit volume, Z represents the atomic number, here T represents kinetic energy, A represents the radius, and D also represents the radius of the cylindrical shell. Now from this equation we know the value of T. Okay, you know the value of T. What is the value of T? From equation 5. Okay, T is nothing but Z square e power 4 by 8 pi square epsilon naught A square V square into M naught. So since from equation 5 we know the value of T. and substituting the t value in this equation. So what you will get, ma? Minus dE by dx is equal to 2 pi nz. Okay, integral a minimum to a maximum. Okay, what is t value, ma? From equation 5, that is z square e power 4 by 8 pi square epsilon naught a square v square into m naught. Then a into dA is there. So a into dA. Just I have substituted equation 5 in this equation. Then we got minus dE by dx. Why we are representing this equation with minus? Because we are considering the loss of energy per unit path of length. So we are representing it with minus. So minus dE by dx is equal to 2 pi nz integral z square e power 4 by 8 pi square epsilon naught a square v square into m naught. So in this equation you know each and every parameter into a into dA. Now I am going to bring this z square e power 4 by 8 pi square epsilon naught a square v square into m naught out of the integral. Okay, I am going to bring this whole term out of the integral. By substituting t value, that is kinetic energy, in the energy lost per equation, then we got minus dE by dx is equal to 2 pi nz integral a minimum to a maximum z square e power 4 by 8 pi square epsilon naught square a square v square into m naught a into dA. So from this equation we are going to bring this whole term out of integral. Then what we will get here? Minus dE by dx is equal to 2 pi nz, like that only, z square e power 4 by 8 pi square epsilon naught square a square v square into m naught into integral a minimum to a maximum a into dA. Now here from this equation what gets cancelled here? Here square and pi gets cancelled. 2 ones are 2 fours are. Okay, that's it. Now the remaining terms I am going to write here. That is minus dE by dx is equal to z square minus dE by dx is equal to the remaining terms I am going to write here. That is z square e power 4 into nz by 4 pi epsilon naught square a square v square m naught into integral a minimum to a maximum a into dA. Now here also a gets cancelled, a and square gets cancelled, and the remaining terms I am going to write. Okay, so what you will get here? Minus dE by dx is equal to z square e power 4 nz by 4 pi epsilon naught square v square m naught into integral a minimum to a maximum. Here a and square gets cancelled. dA by a will be remained. So dA by a. Now integral a minimum to a maximum dA by a can be written as log e A maximum by A minimum. So overall energy lost per unit length of cylindrical shell is given by minus dE by dx is equal to z square e power 4 nz by 4 pi epsilon naught square. Okay, v square m naught into this whole term can be written as log e A maximum by A minimum. Consider this as equation number 6. Now the lower limit, that is A minimum, can be obtained by the uncertainty principle. Okay, so uncertainty principle is given by delta x delta px greater than or equal to h. According to the uncertainty principle, we have delta x into delta x into delta px greater than or equal to h, and A minimum into 2m naught v greater than or equal to h. That means delta px. In place of that, we are going to substitute 2m naught v. So in any elastic collision, it is impossible to change the momentum of electron by amount the greater than 2m naught v. So overall A minimum, okay, A minimum can be given by the equation h by 2m naught nu, and A maximum is given by nu by v, and A maximum is given by nu by v. Here nu, I am saying, this nu represents the average of frequencies of oscillation of the electron in an atom. That is, average frequencies of oscillation of the electron in an atom can be given by nu. Substituting the values of A maximum and A minimum in equation 6. So by substituting A minimum and A maximum in equation 6, what we will get now? Minus dE by dx is equal to z square e power 4 nz by 4 pi epsilon naught square, okay, v square m naught into log e. What is A maximum value? Nu by v. Nu by v by A minimum value h by 2m naught nu. Okay, so overall, how can you write this? Minus dE by dx is equal to z square e power 4 nz by 4 pi epsilon naught square v square m naught. Here m naught represents the mass of electron into log e nu by v into 2m naught nu by h. Okay, so by substituting those things, A minimum and A maximum, finally we got this equation. So here 2m naught nu is there, here nu is there, so you can get it as minus dE by dx is equal to z square e power 4 nz by z square e power 4 nz by 4 pi epsilon naught square v square m naught into log 2m naught, like that only, nu into nu square by vh, okay, or h nu. Here m naught you are observing, m naught is the mass of electron, m naught is mass of electron, okay, and dE by dx dx we are saying. dE by dx is the stopping power of medium, and h nu is nothing but average excitation energy or binding energy of atomic electron. Okay, this h nu is equal to I. I is nothing but ionization potential. Okay, so here h nu related to the ionization potential, and it is given by I is equal to 9.1 Z of 1 plus 1.9 Z to the power of minus 2 by 3 electron volt. So this equation 7, okay, this we are saying it as equation number 7. This equation 7 is referred as Bohr's formula for low speed moving electrons. Okay, equation 7 represents Bohr's formula for low speed moving electrons. Low speed electrons. Okay, this is about the Bohr's theory. By this we have completed Bohr's theory. Once again I am repeating, we are in Bohr's theory. In previous lecture we have solved up to equation 5. Then continuation of that is carried by today. So after completion of equation 5, that is T value, then we have considered a cylindrical shell. That cylindrical shell is composed of electrons. Okay. Now we have assumed the radii of cylindrical shell, and they are given as A and A plus dA. And we have considered the length of the cylindrical shell. Length of the cylindrical shell we have denoted as dx. Then we have assumed that, we have considered that the transfer of energy from the charged particle Ze to the electrons present in the shell. Okay, now our aim is to derive how this charged particle Ze is sharing or transferring energy to the electrons present in the shell. Okay, so to find that, we have considered the equation, that is dE is equal to 2 pi n. Okay, now 2 pi n Za dA dx into T. Now, while it is transferring, okay, there will be loss per unit path length of the particle. That energy loss per unit path of particle can be given as minus dE by dx, and it is denoted by, okay, 2 pi nz integral A minimum to A maximum dA dA. And you know the value of T from equation 5. So we have substituted the value of T. Then we got this equation. Now from this equation I brought this whole term out of the integral. Then some terms gets cancelled here. 2 ones are 2 fours are, and pi and square gets cancelled. And even here A and here also A square is there. A and square gets cancelled. The remaining terms I have written, and dA like that only. Here A and square gets cancelled. Only one A is present in the denominator. So I have written in the denominator term. After cancellation, the overall term is this. Okay, integral A minimum to A maximum dA by A can be written as, that means 1 by A into dA is nothing but log A maximum by A minimum. Then we have considered the uncertainty principle. Okay, it is not possible to calculate the position and momentum for any particle at any instant of time. So according to that, we have equation delta x into delta px greater than or equal to h. So from that we have given the calculated the A minimum and A maximum. A minimum is given by h by 2 m naught nu, okay, and A maximum is equal to nu by v, okay. Then by substituting those things we got this equation. From this we know each and every parameter. Here m naught is mass of the electron, okay, h nu is equal to I. Here I represents the, okay, here h nu is equal to I. I is nothing but average excitation energy or binding energy of atomic electron of any medium, and it is related to the ionization potential of the stopping material. So the mean ionization potential is given by I is equal to 9.1 Z of 1 plus 1.9 Z to the power of minus 2 by 3 electron volt. This equation represents the Bohr's formula for slow speed moving electrons. In the next class, we are going to know about Bette's formula, and Bette's formula is used for knowing the speed of high speed particles, okay, velocity of high speed particles. Thank you.